are office hours. There are office hours this afternoon. Claire can jump in and tell me what time they are.
They are at, I'm trying to not mix up today and tomorrow. They are at 7 until 8.
So if you are organized with your team, that would be a lovely time to actually start the assignment that's not due for a little while. Remember what I said about play? You'll do the best job of learning if you've got a little bit more time on your hands. And I recognize, I'm fully aware you're busy students and you got multiple courses pulling on you. Okay, so you gave me some feedback last time about with some questions after last lecture. And so I went through and made some changes to kind of recognize that. The first question had to do with this whole question about which causes more drag, and there was a confusion about what the shape of the object was. And I realized, oh my goodness, I've been using PowerPoint all these years for decades. And so images are out of PowerPoint, and I realized, but I also now have Onshape, and so I can make objects that actually look three-dimensional, even though they're flat on the screen. And so there's the bowl. I hope it's clear now what it is that we're orienting in both directions. And so when the air is blowing into the bowl or the water is blowing into the bowl, it's very different whether it's facing where the air is hitting the round side, like I've shown here, or the other one, which the air is going into the bowl and then back out and around 180-degree bend. And that bend that is so sharp ends up resulting in streamlines coming very close together. Streamlines close together means the velocity is high. Velocity is high from Bernoulli equation means the pressure is low. And that means there's lots of drag on the backside of that object. Okay, so that was that. The other thing that I ended up doing is I realized that these two equations are confusing. So let me go through those two equations again, the Bernoulli and the control volume energy equation. So the Bernoulli equation is along a streamline. So anywhere along a streamline, we can take 2 points and can figure out what changes based on the fact that the Bernoulli equation is true between those 2 points with all those caveats. And I updated my equations to be clearer that V is not a capital V. It's a small v representing it's a point. It's a velocity at a point. It's not at a surface. It's not some average value. It's at a point. And okay, so that's that. The control volume equation is, now I put a pipe up there, a pipe system, and the control volume is from some control surface in to some control surface out. Okay, so in the control volume equation, you have no idea what's happening inside that control volume. The control volume equation doesn't tell you anything about what's going on inside that control volume. You're tracking what's going in and what's going out, and then doing the math on hence what must on average be happening inside. But you don't get any detail about what's happening inside. So the control volume is all the fluid between the two control surfaces, between the two blue surfaces that I've drawn. You're tracking energy in and out. So there's the equation. And this time, you know, you can go into details. Like P in is the pressure at the centroid of the control surface. So it has a very specific meaning. It's the pressure at the centroid of the control surface. V in is the average velocity through the control surface. And in this very fully detailed energy equation that I've shown here, there's even an alpha out front of the velocity term to correct for the fact that the velocity isn't uniform. And so the average of the velocity does not equal that. The average velocity squared does not get you the average kinetic energy. Oof, that one may give you a headache. But because the average velocity squared does not give you the same as the average of v squared, that alpha term shows up as a correction for the energy term. But the big thing is that v, here is a big V. I put a bar over it to just like drive the point home. That is an average velocity, not a point velocity. And so then we can take measurements at the two control surfaces and like the pressure and the elevation and the velocity. And from that, we can figure out what the head loss is, assuming that there's no pump and no turbine in the system. And that head loss is basically a measure of mechanical energy that's been converted to heat. So it's lost mechanical energy. So here's another difference, and I realize this slide now has too much information on, but there we go. The control volume equation is not reversible. There's an in and an out. In happens before out happens if you were following the fluid through. So it's irreversible. Whereas the Bernoulli equation, because it's a frictionless system, it doesn't really matter which you call point 1 and point 2. There's no sign difference. You see that? You can reverse the Bernoulli equation and nothing exciting happens. It's all legal. So you can switch 1 and 2 and it's all legit. You can't do that in the control volume equation because head loss is an irreversible process. And I just want to stress here that you can't use the Bernoulli equation through a flow expansion. You can use it in a flow contraction, and that's what it's actually really good at, but not in a flow expansion where the fluid is slowing down, and as it's slowing down, it's heading off in different directions and it's becoming chaotic, and that chaotic flow is just generating eddies that are ultimately spinning down and ultimately just causing the fluid to deform a little bit, and viscosity ends up showing up and turning that deformation into heat. Anybody want to ask a question on that? About Bernoulli versus control volume equation, the energy equation? Okay. I want to get to what did we, oh, I guess, did I change this graphic too? Like the first thing I did after our meeting last time was like go through and recreate graphics to make them clearer. I think I already had done that, and we are now ready for this equation, this question, I believe. And you know, I'm tempted, Patrick, let's just do these questions. This first one we can just do with raise of hands because it's just 2. So you've got a long streamlined train, and you're going to compare that with a long straight pipeline. And they're similar in some way. They both have significant energy losses due to shear between the fluid and the solid surface, or they both have significant energy losses due to flow expansions. So which one is it? A long train and a long pipeline, where are they losing their energy? So who wants to vote for 1? Raise your hand, 1. Don't be shy. And I'm seeing 1, 2, 3, 4. Boy, it's hard to count on Zoom. Do you figure it out, Claire?
Around 12.
Okay. Okay, and now for the number 2, they both have significant energy losses due to flow expansions. Who wants to vote for that one?
Three or 4 or so.
Okay, so science by consensus wins in this case. It actually is number 1 with long streamlined body or long straight pipeline. The losses are due to shear on the wall. That is the definition of major losses. And And it takes a long pipeline and a long streamline train for those losses to become significant. A tractor trailer doesn't cut it. A tractor trailer, the big losses are the huge wake behind the tractor trailer. But if you had streamlined tractor trailers, actually the bottom geometry of tractor trailers is awful. But this train is a nice indication of there's a long streamlined surface. So let's talk about those major losses, the losses that are due to wall shear. Here's the equation that describes it. Whoa, hang on. The equation is the Darcy-Weisbach equation. So Darcy-Weisbach came up with this equation. You probably used this in fluids at some point to calculate head loss in a pipe. And I wrote it in two forms. In the second form, I just got rid of V and put in Q divided by A, and I got rid of A. A is pi d squared over 4. So if you make all those substitutions, you get from the equation based on V to the equation based on Q. The equation based on V is more beautiful in some ways. It's simple. The equation based on Q is what you would actually use if you were working with a pipe. So how do we get that friction factor? That friction factor is kind of the elusive parameter here. So the friction factor is going to be a function of the Reynolds number. Reynolds number is a measure of the force of inertia divided by the force of viscosity. So it's a ratio of those two forces. So if inertia is large compared with viscosity, then you have a high Reynolds number. And at some point, it means that viscosity is not even a significant force to deal with. Does that make sense? If you've got this dimensionless ratio of two forces, and the top force is inertia, the bottom force is viscosity. And if inertia is huge compared with viscosity, it's a big Reynolds number. And it means that viscosity isn't even significant in the problem. And you can just forget about it. Okay, and actually that'll show up when we look at the Moody diagram, you'll be able to see that. The transition from laminar to turbulent occurs at around 2000 for pipes. So here are the two equations for head loss in a long straight tube or pipe. This is a head loss due to shear on the walls for the major losses. So for laminar flow, we get this beautiful equation that's 6, that the friction factor is equal to 64 divided by the Reynolds number. That's kind of cool that it was that beautiful. And you get the Hagen-Poiseuille equation when you plug that F into the Darcy-Weisbach equation from the previous slide, you get Hagen-Poiseuille. Okay, so no magic. Take the Darcy-Weisbach equation from the previous slide, plug in F, and also plug in what the Reynolds number is, V times D over nu, and you get the Hagen-Poiseuille equation. So Hagen-Poiseuille is a really nice equation and one that we're going to use because under conditions of laminar flow, the relationship between head loss due to shear friction on the walls, is directly proportional to the velocity in the tube, the average velocity. So here, that big V in the Hagen-Poiseuille equation, remember, these are control volume equations. And so the V is an average velocity at a control surface. So it's proportional. Head loss is proportional to V. And if we go to the other side, for turbulent flow, then all of a sudden it gets ugly. So here's an equation for F. It's a mess, but there it is. Epsilon is the wall roughness, and there's no beautiful simple equation for we don't get a Hagen-Poiseuille kind of equation out because F is such a mess. So we keep the Darcy-Weisbach equation and just say, we're going to do this in 2 steps, calculate F, and then plug it into Darcy-Weisbach to get the head loss. Okay, and you've all seen this, the Moody diagram. You've used this equation, or sorry, you used this graph to solve a problem in fluids, yes? Okay, you know what that means? It means that all of you have used the Moody diagram to solve a problem more recently than I have. Could ponder that one. So what do we see? First of all, over here, where the Reynolds number is less than 2000, we have this lovely straight line. That's the Hagen-Poiseuille equation, where we plugged in this F equals 64 over the Reynolds number into the Darcy-Weisbach equation and have this beautiful straight line. That's lovely. And then the rest of the graph is a series of curves, each one for a different roughness of the pipe. So the smooth pipe is all the way here in the bottom, having the lowest friction factor possible. And as you get rougher and rougher, you go higher and higher up on the graph. And what you notice is that all of these lines go flat. So they all eventually are level on this graph, which means that the friction factor takes on a constant value. Remember, I just said that at high Reynolds numbers, a high Reynolds number means that inertia, or the effective velocity and density, inertia is big and viscosity is small. And that means that viscosity is insignificant. Reynolds number is our measure of whether or not Reynolds number is a measure of whether or not viscosity is significant. At high Reynolds number, viscosity isn't significant anymore. And so there's no longer any change in these curves. They go flat because the only thing that matters is inertia, and that's kind of constant. The question I have is, oh, I should have changed these to numbers. I'm going to do that very quickly. Hang on. Going to try to change these to numbers. I want you to think about this next question. Okay, now. And I've got to share again. So here's the question. Head loss through a long, rough pipe with turbulent flow. So we're in turbulent flow, you've got a long, rough pipe, and I'd like to know, how does head loss vary? Does it decrease? Does head loss decrease if the flow increases? Does head loss remain constant? Does head loss increase in proportion to the flow? Does it increase in proportion to the square of the flow? Or does it increase in proportion to the natural log of the flow? And I want to give you, goodness, like give you 2 minutes to ponder that one, okay? How does head loss vary in a long, rough pipe? And thank you, Patrick, for a speedy poll. Okay, I'm gonna encourage you to take a shot at it. Take your best guess, and then we'll discuss what actually happens. So go ahead and vote. Thank you. Thank you, Claire. So how do you design a pipe using the Moody diagram? So supposing I want a pipe that transports 10 liters per second of water at a distance of 100 meters, so over a distance of 100 meters in a pipe, and I'd like to have less than 1 meter of head loss. So I want HF to be less than 1 meter, maybe HL. HL standing for all the head loss, HF, the friction, wall shear, major losses, HE, expansions, minor losses. I want a pipe that transports this and has less than 1 meter of head loss. So what do I do next? I could assume an F for the Moody diagram. And from that, I can take the Darcy-Weisbach equation written out for Q, and I can solve that equation for D. So this Darcy-Weisbach equation, I can solve that for D, and then I get some random diameter. And then I can look at my pipes that I can buy at the hardware store, and I can round that diameter up to the next bigger size of internal diameter of pipes that I can actually buy. So round up to the next available pipe size. And then I can calculate the actual V in my pipe, given that flow. And I can then take that and calculate the Reynolds number. So I got the V, given the actual pipe that I have and the flow that I'm forcing through it, 10 liters per second. I calculate the Reynolds number, and then I can go back to the Moody diagram and I can find F. And because I started with an estimate, and so then I go around in a circle and I just keep on looping until it converges. Happily, it converges really fast, but unhappily, like what a mess, right? All these steps just to design a pipe. And we're going to be designing, or at least in designing a water treatment plant, you end up designing many, many pipes. And so well, this is where our motto or our mantra of if it's hard, there's probably a better way. And the Moody diagram is hard to use. So there's probably a better way. So I haven't used the Moody diagram in decades, and I would urge you to stop using it too. Okay, it is useful as an educational tool to look at what it actually looks like, but it is not a useful tool for solving engineering problems. You could either use our functions in FeatureScript or in Python to run through this. There are others out there that have created similar tools. There are equations that essentially replicate the entire Moody diagram in equation form. The Swami-Jain equations are some of those. And they make it possible to just solve this with a nice piece of computer code. We want tools that allow us to design so that when we change an input, the design updates automatically. So do you see this problem? If you use the Moody diagram as a step in your design process, it means that when the client comes back and says, you know what, that flow that we were designing for, we've done another piece of our study and we realize that we need to increase the flow by 20% to meet future demand. And if you use the Moody diagram to design your system, you have to go back and do Moody diagram all over again for all the pipes in your system. But if you use computer code that replicates what the Moody diagram does, then you just change the flow rate in your design and everything updates automatically. And a few seconds later, you have your new design. So that is the design process that I am excited about teaching, is a process where if I came back and told you that I'm not going to actually tell you the flow rate that you need to design this homework, this design challenge for, but I'll tell you 5 minutes before you hand it in what the flow rate is, you should be like, oh, piece of cake. I'll just enter into flow right when Monroe tells me at the end. You see the power of that method? You basically have solved all the problems at once, and all you have to do is change your inputs. Another thing that I want in a good design tool is I want a design tool that handles units. And I know that many practicing engineers use a wealth of Excel sheets to do calculations. And for those of you going out into the consulting world, you have to at least know enough Excel to know you're going to get into that. And so, yeah, you should know how to use Excel. But it is, from my perspective, an awful way of doing design work. I long ago began refusing to look at people's Excel sheets because the probability of there being a unit error in the Excel sheet is just so high. It's just predictable. There will be a unit error because unit conversions are embedded in cells in awkward ways, and there's no easy way to check it. So what would a good tool do? A good tool, you should use units for your design. The tool itself should use those units. And at the end, you should be able to say what units you want the results to be in, and it should just give you the units that you want. So the reason that it's so powerful to have the software tool that you're using actually handle units is that means that you can't write any equations that aren't dimensionally correct. So if you write the Darcy-Weisbach equation and where it says v squared, you forget to square the v, it will throw an error immediately and say your units don't match. And that's one additional check that you get by working in an environment where it's actually using the units as part of the calculation. Forces you to use dimensionally correct equations. And we'd also like to be able to create modular code that once you solve the head loss equations once, those equations should just be there for you to use. The next time, you shouldn't be scrambling around and figuring out how to recreate that wheel. So minor losses. So that was all about major losses in Moody diagram and wall shear. The other kind of loss that is very, very significant is losses due to expansions. So these losses happen when the velocity decreases and some of the kinetic energy is converted to heat. We can minimize losses by using gradual expansions. There's the form of the equation. Head loss due to minor losses is equal to some minor loss coefficient times v squared over 2g. And v, this is a little bit weird to think about, but v is some characteristic velocity. It could be the velocity where the flow is contracted. It could be where the flow is fully expanded, or it could indeed be some other convenient velocity. The important thing is that you know what that velocity is referenced to, and that you make sure that your minor loss coefficient is calculated for that characteristic velocity. So here's an example of using that. This is a flow expansion. The derivation for this is in the notes, and you can see how this is like the one minor loss that you can calculate from first principles and get an exact solution. So for this sudden flow expansion. So there's three different ways that I have it expressed here. The last two, the first one is like the exact solution. The last two show using a minor loss coefficient to express that loss, and you can either have it go with the velocity, the high velocity in the contraction, V in, or the lower velocity, V out. And what changes is your definition of the minor loss coefficient changes. So that if you've done this right, when you calculate the head loss, you get the same value with either set of equations. That's the one that we use most commonly. And I was reflecting, we have a case in the flocculator design where the flow doesn't actually ever fully expand. And so the flow doesn't actually occupy all the space that's between the baffles in the flocculator. And yet we use the velocity that would occur if the flow were fully expanded. So it's this idea that V is some representative characteristic velocity as long as you know what it is and you make sure that your minor loss coefficient is scaling with that. Okay, so here's an example of an elbow. So water flowing around this 90-degree bend. And where is in and out in this? So where is in and out in that's similar to what we show here with this expansion. Because flow through an elbow is actually a combination of a contraction, which now you know is a very efficient process, followed by an expansion. So the expansion part in the elbow, where is it? Where's in for the expansion part? So B is where the flow is fully contracted. That's like this part right here in this flow expansion. That's where it's fully contracted. And C is where it's fully expanded. So you can think of this as exactly the same as a regular flow expansion, just that we don't know exactly what the velocity is in B because we don't know exactly how much it's contracted. See our problem? But what I want to drive home is that every time there's a minor loss, it's because there's a flow expansion buried somewhere in the system. And I'm showing you very clearly where this flow expansion is inside this elbow. You good with that? There's a flow expansion there, and that's where the losses are. See, before I suspect, like when I took fluids and when you took fluids, you had this notion that there are minor losses, but it wasn't clear like what is actually causing all those losses. And you learned that there were minor losses in contractions and there are minor losses in expansions. Now you know there are minor losses in expansions, period. It's just that there are expansions inside contractions. And there are like in a contraction, there's an expansion right after the contraction because there's a vena contracta at the contraction. So it looks like I already answered that question. So these are these two forms of the equation for an expansion, either KE or KE prime. Here's a question for you. What is the value of KE? So using the equations that I've circled in red, what is the value of KE for a case of a pipe discharging into a lake? So small pipe discharging into big lake. What's KE? You can do the math. What's A out over AN for that case? You're comparing a lake to a pipe, and the lake is A out. So A out over AN is approximately what? Anyone brave enough?
That term goes to 0.
That term goes to 0, exactly, thank you. And so that means that KE goes to 1. And you know what, like, and the physics, it means that if you take a pipe and you have it dumping into the lake, like, but where it's injecting right into the lake, all of the kinetic energy from that pipe is lost. 1, all of it. Got it? V squared over 2G is the kinetic energy that pipe has, and that kinetic energy is just turned into turbulence and then heat in the lake. So now if KE equals 1 means that we lost all of the kinetic energy, what does it mean when KE exceeds 1? Oof. So if KE is bigger than 1, this is that trick that, remember, our velocity is some characteristic velocity. And so maybe we weren't using the velocity that was actually happening, because it wouldn't make sense to lose more kinetic energy than what's actually there. But if the V that was actually there was greater than the characteristic velocity that we were using to scale the K, we could have this apparent thing where KE can exceed 1. And this is actually very common. So it means that we're using a slower velocity as our characteristic velocity than what's actually losing the energy. And so here's a case of that. Take this gate valve. If you were calculating the K for flow through the gate valve, the only velocity that you can calculate is based on the diameter of the opening, or the diameter of the pipe opening, whichever you prefer. And because you don't know how far closed this gate valve is going to be. So that means that your K value is based on this velocity of the flow through the entire pipe, but it is possible to close that gate valve down a whole lot. And that means that the velocity in the pipe can be tiny compared with the velocity squirting through the opening in the gate valve. Yes? So when the water is squirting through a small opening in the gate valve, the amount of kinetic energy that we're losing is related to the velocity of that water squared times 2g. But because we're using the velocity over the entire area of the pipe, that velocity is a lot tinier. And that means that we're going to use a K that is a whole lot bigger than 1. So it is very, very possible to have a K that is hundreds or even thousands. It just means that you're using flow through, you're pretending that the flow is going through something like this, and you're using your velocity from that, when actually the water is going through some tiny hole. Anybody want to ask a question there about this idea that K can be much, much bigger than 1? Because we're not actually using the velocity that's happening to scale the minor losses? I have a question. Man, like, are you like, it's okay, continue, or you want to talk about this? Like, would you like to talk to a partner about this?
I have so the more and more you close that valve, essentially your KE essentially goes to infinity. Because
that's right.
Okay, all right.
The velocity of the water coming out of that tiny little gap goes up and up and up. Okay. So what do you think? We're going to drain water through a little valve, and you can see the valve in the bottom here for this tank. And there are 4 sedimentation tanks here. Each tank is a separate unit. So we're trying to drain one of those, like 1/4 of this whole unit, through this valve. And I also show another view in the back here. And I'd like you to just like think about, based on what we learned so far, what do you think? Is this a problem where major losses dominate, minor losses dominate, or those two must be equal? And as a reminder, major losses is about shear on the wall. Minor losses are about flow expansions. And don't take long. Let's just vote, and then we'll talk about this. You guys are great. You are exactly right. Minor losses dominate. And I'm wondering how you think about this. how do you think about which ones dominate? Because this, like, the truth is, the answer could be, I need to go do some math, right? I need to do some calculations and check this out. So that's actually a really good answer, but I need to go do some math. And the question is, like, what would the math be that you would want to do quickly to figure this out? If we look at the two equations for minor loss and major loss, they're so similar. There's major loss, there's minor loss. So what are we actually comparing? Given that the velocities are the same in both of them, we're just comparing which is bigger, FL over D or KE. And if you knew which one was bigger, you know which one dominates. And then the question is, well, what's KE? So for this pipe, there had to be an entrance somewhere. There's an exit where it's just dumping out and all that energy is lost. And there's the valve, and there's going to be some losses through the valve. Net is that at least you lose all the energy coming out the end of the pipe. So that's a K of 1. And so the question is FL over D greater than 1? And so an interesting idea is that F is on the order of 0.02, so 1/50th. And that means that if L is more than 50 times greater than D, then major losses have a chance of dominating. But if FL over D is less than, if L over D is less than 50, then chances are minor losses dominate. Of course, you should know what the minor losses really are, but it takes a lot of length of pipe to get you the same thing as just the fact that the pipe is exiting into the atmosphere and you're losing all that energy. So good job on that. Here's another thing about using the energy equation, and it's a trick that's about thinking about how we apply the control surfaces in the energy equation. So here's a tank. It's got a little hose connected to it, a small diameter tube. And we'd like to know how much water is going to flow through that hose. So we're going to apply the energy equation, and we're hoping that we can figure something out from that. And so let's look at this. So let's try this case where we're going to put a control surface for our control volume right at the beginning of the pipe, and another one somewhere where I'd like to get the velocities to cancel out. Because see the problem? I'd like to know what the velocity is through this pipe. I'd like to know what the flow rate is. So I need to know what the velocity is. And in the energy equation, the velocity is showing up, and I'd like that to cancel out somehow, because I want to get the energy equation to give me the head loss so that I can use that in the Darcy-Weisbach or Hagen-Poiseuille equation to figure out what the flow rate is. So I'd like the velocities to cancel out in the energy equation. So how could I get the velocities to cancel out? Well, I could put the second control surface right there, right? And now V in is the same as V out. And so I can cancel all those things out, and I'm, oh shucks. What do I do about P in? What's P in? Well, you're most certainly very tempted to say, well, that's rho GH. I can just take the height of water, H, and multiply that times rho G, right? Does that make sense? But there's an I gotcha here, because the pressure at that control surface is not just due to rho GH. The water is accelerating as it's going through that control surface. It's got some velocity, and that means that this isn't a statics problem. So we can't use rho GH, I'm sorry to report, to calculate the pressure at the control surface. You see how that problem evolved? I wanted to figure out the pressure at that control surface, and I don't know what it is because it's not a statics problem. I need to know what the velocity is through that control surface in order to figure out what the pressure. Oh, and which equation would I use? I could use Bernoulli equation because it is an acceleration into that control surface, but I don't know V, and so my problem just got worse. Okay, so this was actually a really bad path. So somehow I selected the wrong control surfaces. Did you ever wonder about this in fluids? Like, did you get the sense that figuring out where to put the control surfaces was not easy? Anyway, let's try again. So that was fail. So let's add the tank to my control volume. So now I'm putting the surface at the top of the tank. And what this does is it makes V1 go to 0. It's a big tank, okay? Kind of like the lake. So then where can I put the out control surface so there's no velocity? And this is where we get yet another problem. So we're going to do a trick. We're going to add an imaginary water surface right there. And I'm going to say this water is flowing into the very top of a tank. And I'm going to put my control surface on top of that tank. Okay? I don't actually need the tank. I just needed a horizontal control surface. And now the velocity through that control surface is also 0. But now, what are the minor? So my energy equation is now easy to solve, and I'm going to get that the head loss is equal to the elevation difference, which I've shown there on the graph already, or in the drawing. And my control volume is all that stuff in blue. So now what's the minor losses? So we have our control volume equation, and we have a second set of equations, which is the Darcy-Weisbach equation that is dimensionally correct, but that and we also have the minor loss equation where it's the sum of K times V squared over 2G. And then the total head loss comes from those two. So let's try this. We're going to cross out all the terms that we know. We're going to get delta Z. Oh, this was stage 1. This is what happens if I draw the control surface vertical on the effluent line. You see that? If the effluent line has a vertical surface on it and the water is flowing through that surface, then I get delta Z equals V squared over 2G plus head loss. And I don't get this beautiful equation for head loss. So what we do when we flip the control surface from here to here, what we've done is we've moved that V out into a K. That change in velocity, that loss of kinetic energy, becomes inside our control volume, because our control volume exit has 0 velocity. So the change in energy as the water is exiting the pipe and falling into this big lake or tank, that energy loss is inside my control volume. And so I need to add that K to my minor loss coefficient. And so that means that my minor loss coefficient increases by 1 because I have that K from losing all that kinetic energy as the water exits the pipe. And in that case, delta Z is just equal to head loss. And I have these set of 3 equations, and I just have to remember that my exit loss goes in the minor loss equation as well. And that makes solving this kind of problem really, really easy. And that's something that we will do plenty of times in this course. That method is also described in the textbook. Anybody want to ask a question about that? The trick was I moved the control surface to a place where the velocity was 0 and put that kinetic energy loss from the velocity that it had to that 0 velocity as an extra minor loss coefficient. I feel like I see some puzzled brows. Anybody want to ask a question? We'll have office hours. You can stop by and ask then too, if you prefer that. Happy to talk about this more. So here's a system in India where we're taking water from a well. There's a solar powered pump down in that well that's lifting the water up out of the well and all the way up into a water treatment plant that is sitting on top of a storage tank so that the water gets treated, then goes into the storage tank, and from there goes to the community, the village, with a piped water system. And the question for you is, will the pump be able to lift more water up to the tank if the vertical pipe, so the vertical pipe is the section running up the side of the tank. Will the pump be able to lift more water up to the tank if the vertical pipe is smaller in diameter? Yes or no? Happy to take your votes. Shall we do a vote by hand or poll? Is Patrick almost there with a poll? Or a hand is fine. It's going. This is great. So you should know that so if we make the vertical pipe smaller, the consensus is that we'll be able to pump more water up into that tank. You should know that this is a very, very common misunderstanding about fluids. And it is not true. So what's going on here? Here's one way to think about when Monroe poses a question like this, a way to think about it that will in general help you figure out the answer. And that is to be an extremist. Take Monroe's question and apply the most extreme option possible. So here I just said if the vertical pipe is smaller diameter, so make that smaller pipe really, really, really tiny. Would you change your answer now? Like I take that diameter and I drive it to 0. At some point, that pump's not going to be able to pump any water through that pipe. I'm asking this question correctly, right? Right, Claire? So what is the pump actually experience? So there's this common misunderstanding that the big pipe of water is somehow makes the pump struggle, but it doesn't. You could have the pump, you could have the tank extend all the way down to the ground and the pipe from the pump just go into the bottom of that tank. Would that be easier for the pump or harder for the pump? Do you get my new case? we have the tank. The elevated tank is no longer elevated. It's now sitting on the ground and it comes all the way down. And the pipe that's coming from the well just goes right into the bottom of that tank. Is that harder for the pump? And the answer is no, that's easier for the pump. So what actually makes it hard for the pump? The pump is experiencing pressure. And where's the pressure coming from? There's two things that are causing the pump to experience pressure. One is the hydrostatic head, which is basically the elevation of water in the tank, or at where it's entering into the water treatment plant at the top of that building, to the level in the well. And that elevation difference between the top where the pipe discharges and the well is a pressure that the pump has to be able to provide or lift. And then there's one more source of pressure, and that is head loss. So any friction or expansion losses in the pipe also increase the pressure that the pump is experiencing. So if we make the vertical pipe smaller, the head loss in that vertical pipe increases, and the pump experiences that as additional pressure that it has to overcome to push the flow through the pipe. I have to admit that when I asked this question, I was like, oh, they're all going to get this right. Because I've thought about this stuff for too many decades, and so this just makes sense. But when you're just learning fluids, it doesn't make sense. So the answer is, the bigger the pipe, the more water the pump can pump through it. And the fact that there's this big column of water there, that's not a problem, because the pump isn't even aware of that big column of water. It just sees the pressure. Okay, I've said that enough times. And this comes from a question that students asked in previous years, and that is, how do you get water to go up through a tank by gravity? Like, we have a tank, and this happens in our sedimentation tank. It also happens in our flocculator, where the water is flowing up part of the time. So how do we get water to flow up? By gravity. It seems like by gravity, water should always go down. So here's the problem. Water goes down this pipe, it goes across, it goes down through those little pipes, it ends up turning around and going back up, it goes through the plate settlers, and then eventually it enters little holes in that pipe and it leaves that pipe. So the question is, why did that happen? Why did the water go up? How did we convince, like, did we have a little therapy session with the water beforehand that we talked it and we coaxed it into being willing to go up? How do we pull this off? Okay, so let's take a simpler case. Here's a U-tube. You can think of this as the right side here is my little tank. How do I coax the water in that little tank on the right side to go up? So what happens next if at time zero, I take a picture, and this is what this U-tube looks like at time zero. And let's just suppose that I also took a measurement and velocity right at this moment was 0. Okay, this is possible. What happens next? Someone tell me. Don't be shy.
They're going to even out.
They're going to even out, and they're going to even out by the one on the left is going to go down and the one on the right is going to go up. So we're going to get, but what, and why does this happen? So point 1 is right in the middle of the tube. And I said this was a statics problem because right at this moment, the velocity was 0. So let's see, is this really right? So point 1, the pressure is equal to rho g times h left, but it's also got to be equal to rho g times h right, which means that there's got to be 2 different pressures at point 1, and that can't be true. So actually, this is not a simple statics problem. We'd be violating the laws of physics because you can't have 2 pressures at one point. That's not possible. So this can't be a static situation. And what's happening is at this moment, the flow is accelerating. Yes, the velocity was 0, but it's actually accelerating. And we will eventually get to this equilibrium point, and maybe it'll actually slosh a few times before it actually gets here, but eventually we'd get here. So point was, water's going to go from the side of the tube that's higher, and we can apply that to this tank here, where there's, see the blue lines show up? That's the water level in the inlet, and there's the water level in the outlet. And as long as the inlet is higher than the outlet, water is going to be pushed through this system. And the fact that it has to go up part of the time is irrelevant. Just like getting the water to go up on one side of the U-tube is easily done. The water doesn't care. It's trying to get the pressures to even out. And with that, I'm done. We have 9 minutes left. I'd be happy to take any questions or goodness, I'm done. Anybody want to ask a question?
I'm still confused about the bigger pipe versus the smaller pipe. Just because I thought that it would need more pressure to be able to push the water up if it was a bigger diameter.
Okay, that's great. Thank you for asking that question. And I'm sorry, I was not able to figure out who was actually talking.
It was Tony.
Hi, Tony, thank you. So say the last part again. It would seem that
I just am still confused in regards to the pressure of a bigger pipe, just because I thought there was more area, so more water would be able to fill up the area, meaning more of like a force needed to push it up.
so you're exactly right. The force on the bottom of the pipe is greater, but the pressure is the same. And it's the pressure that the pump has to overcome.
Okay.
What's happened when you have, so supposing we have a stadium full of water, there's this huge force on the bottom of the stadium.
Mm-hmm.
But that force is being carried by the earth, not by the little pump that's pumping water into the bottom of the stadium.
Okay, that makes sense.
Good. See how I took it to an extreme example there? So like, and you could have the tiniest little, weakest little pump pumping water into that stadium and it would still work just fine. Any other questions? In that case,